Look at your left eye in a mirror. Now switch your gaze to your right eye. You cannot see your eyes move. A person standing beside you can see them dart back and forth. A camera can record them. But to your own awareness, the motion seems to vanish. You scan your environment constantly, shifting your gaze to navigate, yet the visual world stays perfectly stable. How does a system in constant, rapid motion hide its own movement from you? Human vision relies on a tiny central region of the retina to see sharp detail. Only a small part of the scene is captured at maximum resolution at any one moment. The rest feels detailed because your eyes keep sampling it, and your brain combines those samples into a stable experience. To gather information about a room, a face, or a page of text, you must constantly point this high-resolution region at different objects. You do this through rapid eye jumps called saccades. You make these jumps roughly 2 to 3 times every second while you are awake. During a saccade, your eye can rotate at hundreds of degrees per second. The movement itself lasts only tens of milliseconds. Because of that speed, the image of the world is swept rapidly across the back of your eye. If human vision worked exactly like a standard video camera, this would create a serious problem. Pan a camera quickly across a room with the shutter open, and the sensor gathers light while the scene is moving. The result is a blurred, smeared image. The retina also integrates light over time. So physically, the rapid sweep of the visual field should reduce contrast and create a brief streak of motion. Several times each second, the walls, faces, and words in front of you should slide across your vision. Yet in daily life, you do not experience that blur. You experience a stationary, coherent world. It is tempting to imagine that the brain simply switches vision off during every saccade. But vision does not shut down. Instead, the visual system undergoes a specific, partial drop in sensitivity known as saccadic suppression. Just before the eye begins to move, visual sensitivity starts to fall. It reaches its lowest point around the beginning of the movement and recovers shortly afterward. This is not complete blindness. Your ability to detect broad shapes and sudden changes in brightness becomes weaker. Color processing is affected much less. The signal is reduced, but the system remains active. In controlled experiments, flashes of light shown around the time of a saccade can go unnoticed consciously, while still producing involuntary responses, such as a small constriction of the pupil. Something can therefore affect the nervous system without appearing in the conscious scene you believe you saw. The visual system continues processing information. It simply does not give every signal equal access to awareness. If the visual feed remains active, why do you not see the smear? A major part of the answer comes from visual masking. In a landmark experiment in 1978, researchers placed participants in darkness and produced a brief flash only while the eyes were moving. Under those artificial conditions, people could see the smeared image created by the saccade. The blur was real. The visual system was capable of detecting it. But under normal lighting, sharp images appear immediately before the eye moves and immediately after it lands. Those clear, stationary views mask much of the faint blur produced in between. The visual system does not need to erase the smear completely. The stronger images around it are usually enough to keep it out of awareness. This is similar to a quiet sound becoming difficult to hear when it is surrounded by louder sounds. The weaker signal still exists, but it loses the competition for conscious attention. Masking is important, but it is not the entire explanation. Researchers still disagree about how much each mechanism contributes. The evidence points to several systems working together. First, part of the dampening can begin inside the eye itself. The sudden sweep of the image can reduce retinal output before the signal travels deeper into the brain. Second, the sharp views before and after the movement hide much of the blur. Third, signals connected to the eye movement help the brain update where objects should appear once the eye lands. Instead of rebuilding the whole scene from nothing, the visual system compares what was present before the movement with what appears afterward. It preserves what seems stable and updates what changed. No single mechanism fully explains the experience. Retinal processing, masking, and movement-related signals solve different parts of the same problem. Together, they allow the eyes to move without making the entire world appear to move with them. This does not produce a perfect copy of reality. It produces a useful, continuous model that remains stable enough for reading, walking, and reach